Hello, thank you for watching this video. So in this video, we're doing question 5 of November 2021, question paper physical science paper 1. This is work, energy and power. So I'll read question 5 statement and then proceed to answer the questions that follow. A 2 kg block is released from rest at point P, 5 meters above the ground. It slides down a smooth, frictionless curved track PQ. See the diagram below. Let me read this thing again. A 2 kg box is released from rest at point P, which is 5 meters above the ground. It slides down the smooth, frictionless, curved track PQ. See the diagram below. So they're saying a 2 kg block, which is this one, is released from rest at point P, and it slides down through this smooth, frictionless, curved surface, right? PQ, which is this, it slides down here from P to Q. That's what it is. And P is 5 meters above the ground, right? And PQ and Q is at the ground, I think. So, no problem. 5.1, state the principle of conservation of mechanical energy in words. So they want us to state the principle of conservation of mechanical energy in words. So, let's take these principles. What is this principle? So, the principle of conservation of mechanical energy states that, it says that if you have an isolated system, the total mechanical energy is conserved, right? So, by being isolated, which means you should not have any other external forces like frictions. As you might have read here, as this thing was gliding down or sliding down this surface, the surface was frictionless there. So, there were no other external forces that were influencing this motion, right? Other than maybe gravity. So gravity was the only force that was influencing this motion. So in an isolated system, so to state this principle of conservation of mechanical energy, we say in an isolated system, which is where there are no external forces, the total mechanical energy is conserved. Let's write that down. Then I'll explain it a bit further. So 5.1, just say that in an isolated system, what does that mean? Isolated system means, which means you have no external forces, external unloaded force, no external forces, or no external unwanted forces. So in an isolated system, the total mechanical energy is conserved. What does conserved mean? I defined it in question 4. Conserved means remain unchanged. So, what this means is that your mechanical energy does not change, right? What is the mechanical energy? Your mechanical energy, EMAC, is what? Is the sum of the kinetic energy and the gravitational potential energy. Which means, you know, your EMAC, this is EMAC, your kinetic energy is half mv squared, and this one is mgh. So, what this means is, if you have an isolated system, if you can calculate the mechanical energy at this point and any other point, it should be the same, which means if you find the sum of the kinetic energy and potential energy here at P, that sum should be the same as maybe at this point here, if the system is isolated. Which means if you have an isolated system, if you sum the kinetic energy of the object at P with its gravitational potential energy at P, it should be the same at any, you should get the exact same sum at any point on this track, somewhere on this track. So in simple terms, You can say, okay, you say your EK plus EP at the starting point should be the same as EK plus EP at any other point. Which means if this is your starting point and maybe you want to find some other stuff here, so you know that if you calculate EP and EK there and EP and EK there, it should come out exactly the same because you have an isolated system. There are no other disturbing forces in this system of yours. So, in simple terms, the principle of conservation of mechanical energy states that in an isolated system where there are no external forces, right, the total mechanical energy is conserved, which means it remains unchanged, which means if you sum it between any 2 points on that system, it should come out exactly the same. That's what this thing means. I think I'm done with this one. So, we'll move to 5.2. What are they saying at 5.2? They're saying, use the principle of conservation of mechanical energy to calculate the speed of the box when it reaches point Q. So, they want us to use this principle that we stated here to find the speed at point Q here. Right? They want us to find the speed at point Q. This is point P. So, we know that we say that this principle states that in an isolated system, the total mechanical energy is conserved, or the total mechanical energy remains unchanged, which means if you sum the mechanical energy at P, it should be the same. If you find your mechanical energy at P and that at Q, it should exactly be the same because the system is isolated, it's undisturbed. So, what we can say is, okay, our mechanical energy at P, at point P, it should be equal to our mechanical energy at Q. Because from P to Q, down along that track, we're told that it's smooth and frictionless. So there are no other external forces that are disturbing our motion there. Right? So, which means we can apply this principle there. We have an isolated system. Right? So, which means our mechanical energy at P, it will be equal to that at Q. What is the mechanical energy at P? It's going to be, I define a mechanical energy as the sum of the kinetic energy and potential gravitational potential energy. So, here we'll have EK plus EP, right? At point P, it should be equal to EK plus EP at point Q. No problem. What is this? This is the kinetic energy, which is half mv squared, right? This is the initial velocity at point Q. Let me say velocity at Q squared plus mg height at Q. Sorry, it should be P. Is equal to half mv velocity at Q squared, because this is point Q, plus half mg h at Q. This is exactly what I've written here, and these are the formulas. Then, what we're looking for is what? We want the final velocity at point Q, because they're saying use the principle of conservation of mechanical energy to calculate the speed of the box when it reaches point Q. So this is what we're looking for. No problem. You just substitute now. So half the mass, what is your mass? It's your 2 kg. 2 times the initial velocity. What was the initial velocity P? Because this is the velocity P. We're told that a 2 kg is released from rest at point P. So the 2 kg block was at rest at point P. So its initial velocity was 0. All squared. Plus m, which is 2. G, which is 9.8. H, which is the height at P. What is the height at P? The height at P is 5. Say 5 here is equal to half m, which is 2, VQ all squared, which is what we're looking for, plus what? Plus M, which is M, your M is 2, your G is 9.8. Your H, what is your H at point Q? The height is 0 here. Because you can see, this is the ground, this is where the 5 was measured from. If you're sitting here, there's no height here. So the height is 0. Then we solve for what? We solve for Q, for VQ squared. So if you punch this alone, you get that this is 0 plus, punch that, so it's 2 times 9.8 times 5. Let me just start that. It's 2 times 9.8 times 2 times 9.8 times 5. This is 98 is equal to half of 2, we have VQ squared, plus punch this, you get that this is 0. My calculator doesn't look very nice, so bear with me. So you take the square root, because these are just zeros, these are gone. So that your velocity at Q is equal to the answer to this. Take the square root of that, it's 9.90 meters per second. That is your velocity, right? It's 9.90 meters per second. We can say to the right. That is your velocity. They only wanted the speed, so there's no need for direction, but here's your velocity. We're done with this. Then we move to another question, which is 5.3. Let's go. They are saying the box passes point Q and moves 10 meters on a rough horizontal surface before striking a barrier at point R at a speed of 4 meters per second. So our box, this box arrived here at a velocity of, this velocity at Q, VQ, the velocity here was 9.90 meters per second, that side, right? And then they're telling us it moved for 10 meters on a rough surface, right? Until it gets here. And when it got here, it did, its final velocity there was 4 meters per second. This is the velocity at which it hit that barrier, because you have the barrier B here, this one. So the box got here at this speed or this velocity, and then it moved for 10 meters on this rough surface and got to the barrier B at that velocity of 4 meters per second, or the speed of 4 meters per second. So that surface is not isolated anymore because there are other forces like friction, other external forces. So let's go. They're saying now, use the energy principles to calculate the magnitude of the average frictional force acting on the box as it moves from Q to P. So they want to calculate the magnitude of the frictional force from point Q to point P. That's what they want. They want the magnitude of the frictional force acting on the block. So what do? We say, okay, the first thing that I'll do, I'll draw the free body diagram of the block anywhere here or on this area. This is how it would look like. You will have the normal force of the surface on the object that is perpendicular to the surface. We have the weight or the force of gravity, and you have the frictional force, which is what they want you to find. They want you to find this guy here, right? No problem. So you normally say that if you want one of these forces like the frictional force, you always say that F net is equal to MA, right? And you know that if you're looking at the horizontal forces, your net force is only going to equal to the frictional force equal to MA. No problem. So you want the magnitude of the average frictional force. You have the mass, but you don't have the acceleration. You don't have the acceleration. So you need the acceleration in order to be able to find this guy here. Because now you have two unknowns. So let's go and find that acceleration. So what do? I say, okay, your Vf squared is equal to your Vi squared plus 2a delta x. So you have your final velocity, which is 4. You have your initial velocity, which was 9.90. You have your displacement, which was 10 units. You want your acceleration here. So it's easy. So okay, 9.90 squared is equal to initial, this was the final velocity, which was 4. Final velocity was 4 because that's what it hit the wall with. This was the initial velocity. Is equal to 9.90 squared plus 2 times a times delta x, which is the displacement. What was your a? So a is a, your displacement was 10. What do? This is 16 is equal to square that. Go to my calculator. So we say 9.90, then you square it. How do we square here? So 9.90 times 9.90. So it's 98.01, or you can just say 98 plus 20a. Right? Then now you have 16 minus 98. It's equal to 20a. So 16 minus 98. So we have minus 82 is equal to 20a. So divide by 20. Divide by 20. So your a is equal to minus 82 divided by 20. Your a is equal to minus 4.1 meters per second. Okay, so now we have our acceleration to be this one. So we said negative frictional force times is equal negative frictional force is equal to mass times acceleration. So what do? We said negative F is equal to mass, which is 2 times acceleration, which is minus 4.1, right? Then your frictional force is equal to 8.2 newtons. This will be a magnitude of the frictional force, going to be 8.2 newtons. Yeah, it should look like this. So the quicker way one would have done it, they could have used the work energy theorem. It would have been much easier. So this one is a bit long, but I like it. So I'm going to do the next one, which is 5.4. So now we're doing the next question. So they're saying the barrier exerts an impulse of 14 Newton seconds to the left on the box when the box strikes the barrier. Let me read this thing again. They are saying the barrier exerts an impulse of 14 Newton seconds to the left on the box when the box strikes the barrier. So 5.4. Calculate the change in kinetic energy of the box after striking the barrier. So they want the change in kinetic energy of the box after striking the barrier. So they're saying now, when this box collided with the wall, right? The wall exerted an impulse of 14 Newton seconds on the box. it exerted that impulse of 14 Newton seconds on the box, right? So they want the change in kinetic energy. They want the change in kinetic energy of the box immediately after it strikes the wall, right? So if you look at that, you can say, okay, my box, here's my box. So during the collision, during the time of contact, you have your normal force, you have your weight or your force of gravity, and then you have the force, you have this force. Now this is during the contact, the force of the wall, right, on your box. This is the free body diagram of this box on the instant of the collision. So you have those forces there, right? No problem. So you know that the impulse, which is equal to F times delta T, causes the change in momentum of the box. So the impulse that was given of 14 Newton seconds will cause the change in momentum of the box, right? So you are given, so F delta T, which is the impulse, is equal to the change in momentum of the box, which is equal to M Vf minus Vi, right? So we can say all forces go on this side are positive and all forces go to the right are negative. Okay, so now what do? We say, okay, we have our impulse is equal to the change in momentum, right? So what is our impulse? Our impulse, we're told that the impulse is equal to 14 Newton seconds to the left. So it's 14 Newton seconds to the left, right? Which means, but we said everything to the left is negative. So we can just say negative 14 Newton seconds. That to the left is the direction of our force that is experienced by our block, which is this one. It's negative. So we said everything to the right is positive, everything to the left is negative. So what do we have? We have negative 14 is equal to M, which is 2, times minus initial velocity, which was 4. And it's going to be positive because it was to the right, because it arrived at 4 meters per second here. So divide by 2, divide by 2. So you get that negative 7 is equal to Vf minus Vi, right? Oh, which is what is your Vi? Your Vi is 4. So your Vf is equal to negative 7 plus 4. So your Vf is equal to negative 3 meters per second. Therefore, your Vf is equal to 3 meters per second to the right, to the left. So this will be your final velocity of the block immediately after the collision. It will be 3 meters per second left. But now what they wanted us to find, the change in kinetic energy. So change in kinetic energy is equal to what? It's going to be equal to final kinetic energy minus initial kinetic energy, which is equal to half m Vf squared minus half m Vi squared. So what we have, you can take mv as a common factor. You can substitute everything here, but half m Vf squared minus Vi squared. So your change in kinetic energy is equal to what? Half the mass, which is what? Which is 2, times final velocity, which is 3, all squared, minus 4, all squared. So therefore your change in kinetic energy is equal to this and this is 1, right? So you have 9 minus 16. So your change in kinetic energy is equal to minus 7 joules. So this is your change in kinetic energy, which they are looking for. So you should be done here. And I hope it does make sense to you, as it does to me. And thank you for watching. Cheers.